Just to give you an overview of method, so ARIMA stands for Auto-Regressive Integrated Moving Average. Okay. Now, so this topic is also somewhat in continuation with what we have been discussing with regards to time series modeling over the past 2 weeks. Okay. So the ARIMA model has 3 components to it. So first one is called as the auto-regression component, and then you have the integrated component, and then you have something called as the moving average component. Okay. So auto-regression is basically the dependent relationship between an observation and some number of lagged observations. So lagged observations means observations which have occurred previously. So lag is defined as lag of 1 period, 2 periods, or 3 periods. Okay. So auto-regressive component basically means for how long does a particular observation depend on the previous observations? Does it depend only on the immediately preceding observation? Does it depend on the previous 2 observations? Does it depend on the previous 3 observations, and so on? So that is what you call as the auto-regression component. And integrated is basically differencing the observations. So if you remember last week, we talked about this concept of stationarity in time series, right? And we said that before implementing this ARIMA model, the time series has to be stationary. And one of the ways to make the non-stationary series as stationary is to take the difference between the observations. Right? So that is what this I component or the integrated component does. Okay. And then there is the third component, which is called as the moving average component, which takes a moving average for a specified window or specified time number of periods. So for example, if you take you can specify something like take the moving average for 2 periods, 3 periods, and so on. So it will take that 2 period or 3 period moving window, and for that particular window it will take the average of the values. So these are the 3 components of the ARIMA model. Now when you actually implement this model in Python, you will have to define 3 parameters, and these 3 parameters are denoted as P, D, and Q. Okay. So first parameter P is corresponds to the auto-regression or the AR component. So it is the number of lag observations included in the model. So this basically specifies each observation is dependent on how many of the previous observations in time. So that is the first component. Next component is the D, that is the number of times that the raw observations are differenced. So that corresponds to this integrated component, differencing the observations. So this is also called as degree of differencing. So do you take the first difference, do you take the second difference, and so on. So differencing is nothing but current observation minus previous observation. So that is the D component. And Q is the size of the moving average window. So for how many periods, subsequent periods of time should you take the moving average? So that is the Q component. Okay. And in this PDQ notation, if you use 0 for any of the parameters, so for example, if you use 0 for P and D, right? So only the Q component if you specify, then it will be called as a moving average model. So the forecast will be a simple moving average forecast for which will consider the number of time windows that you specify. Okay. Or if you use 0 for D and Q, then it will just become an auto-regressive model. Okay. So like that, depending on the different parameters that you specify, or whether you specify 0 or not for any of these 3 parameters, accordingly the configuration of the model will change. So if you just Google for ARIMA, you can also get information about separately how the AR model works, how the moving average model works. And there is also one more model called as ARIMA, so that is ARIMA, because it does not have this differencing component. So like this, based on the parameters you specify, you can adjust the configuration of the model. So this is just to give you an overview of the model's theory. Any questions here? Okay, let me move to the next slide. So for easier comprehension, I have listed down the steps that we will be following to build an ARIMA model in Python. First, we'll be loading the data, and the data that we'll be using is the sample superstore data that we have in Tableau. Okay, and we will perform some kind of a data preparation process. So this is nothing aggregation process. We will it's quite similar to what we saw last week, and then we will visualize the time series, see what it looks like, and then we will visualize the different components of the time series. So the same trend component, the seasonality component, and the noise component. Okay, and then we will perform this ADF test to see whether the data is stationary, and then we will use a looping mechanism to identify the parameters of the model, that is P, D, and Q. Okay, and the way we will use this looping procedure is we will perform different for different combinations of this P, D, and Q. We will perform iterations, and we will choose that particular combination of the P, D, and Q which has the least AIC value. Okay, now AIC stands for KK information criterion. Okay, so what this means is it denotes it quantifies the amount of information lost by a given model. Okay, so the less information a model loses, the higher the quality of that model. Okay, so this is a sort of a relative measure. So I told you we will perform different iterations, multiple iterations, right? So for each of those iterations, we will see the AIC value, and we will take that particular combination which has the minimum AIC value, because that is the model which loses the minimum amount of information. Okay, so minimum amount of information based on what parameters that you specify for P, D, and Q. Okay, and so after identifying the optimal parameters, we will use those parameters to build the ARIMA model, and then we will measure the accuracy of the model, and we will use the model to forecast the time series value for the future periods. So this is the procedure that we'll be following. Any questions until now?
All good from my side, sir.
Okay.
Sai, can you share some real-time applications or use case of this model?
Yeah, so typically you see any supply chain scenario or any planning scenario, the first step to do is forecasting. Okay, so for example, all companies have a procedure called as sales and operations plan, where they lay out something called as an annual operating plan. Okay, so for the next 1 year, how many products do we plan to sell? So if you are planning to sell these many products, given that we already have certain amount of products in our inventory, how many products should we produce? Okay, and this production will also be determined based on the company's capacity, raw material prices, and so on. Okay, and also the market conditions, whether there could possibly be any downtrend in the market for that particular product, or whether the product could see a sudden surge in demand, all those factors. Okay, so in these situations, before starting out on your production plans for a particular year, they make this kind of a forecast, and this forecast is based on the data for previous years. Okay, now I think a couple of weeks we were talking about what is the optimal amount of data that is required for time series forecasting, and then we said it will be good if we had a minimum of 3 years worth of data for forecasting and so on, right? So they take all these factors into account, they take the market conditions and so on, and then they make this forecast. Now the model that we discussed last week, that is the Holt Winters exponential smoothing forecasting model and the ARIMA model, are two of the most used forecasting techniques for any normal time series forecasting. Okay, so this could be something like forecasting the demand for a particular commodity, or forecasting the demand for any particular raw material, or forecasting the price of a share, or these models have applications in different fields. Does that answer the question, Sarah?
Yeah, yes, sir.
Okay, so I will take you through the code now. Just I know that you are familiar with Python and all that, but still I will take you through the code line by line, and also I will send you the script of the code at the end of the session. Now some parts of the code you might not be familiar with it. It has a certain level of combination, but you needn't bother about it too much, because so when it comes to implementation of those things, it is not a mathematically complicated piece, but rather it is just that looping structure and everything, the way we specify that syntax in Python. By practice you will get to know how to do that, do those operations. but just what you need to pay attention to is what sort of a mechanism or what sort of a workflow that we are following to implement this ARIMA model in Python. Okay. So, as I'm sure you are quite familiar by now, the first step before implementing any algorithm in Python is to import whatever libraries that you need for the operations. So first we'll be importing the pandas library, which allows you to work with data frames. And then we import a library called iter tools. So I told you we'll be performing an iteration, right? And we'll be performing multiple iterations. And for each iteration, we will be determining the AIC value, right? So for that looping structure to work in the way we want, we will use this package called as iter tools. Okay. And NumPy, as you know, is used to work with numeric arrays of data. And we will be visualizing the time series, we'll be visualizing the predicted values, we'll be comparing the actual values and the predicted values and so on. For that, we will be using the matplotlib library, the pyplot set of functions. And this particular library, statsmodel.api, basically contains the function which is used for defining the ARIMA model. So that is the thing. Okay, basically repeated the import of the matplotlib library here, just ignore this. And then one other extra thing that we've been doing is, so since we are plotting or visualizing the time series data, we would like to specify the dimensions of those visualizations. Now, this is not a compulsory thing to implement, but I just put it here so that it will be good to know for us. Okay, so this PyLab library has this function called as rc_params, which allows you to specify the different parameters for a chart in Python. Okay, so that is what this is used for. And then we will be measuring the accuracy of the model using this metric, mean absolute percentage error, or MAPE. So that is available in the sklearn library. And I told you we will be checking whether the data is stationary, right? So for that, we will be using this particular package called as AD-Fuller. So this is short for Augmented Dickey-Fuller Test. Okay. So that is why it is specified as AD-Fuller. So once you have loaded all the required libraries in your workspace, the next step to do is we will be defining those parameters for the visualizations. Okay. So we have something called as a plot styles. Okay. So these styles, so they originate from the HTML styles, I believe. I have also not used these styles much, but in HTML or CSS, they have certain definitions for styles. Okay, so and 538 is one of those definitions, which gives you sort of a grid lines and particular shade to the chart and so on. So we'll be using that 538 format, and we'll just apply that format onto our charts in this workflow. Okay. And this is nothing but the labels that we use. So they will have a font size of 14. That is the axis label, and then the x-axis marks, the y-axis marks. So they will be having a font size of 12, and text color K. So this K denotes one particular color, it is the black color. So each color is represented by a particular letter of the alphabet. So that's what we have to say here, and this denotes the overall dimensions of your chart, 18 pixels by 8 pixels.
What if we don't define any of these parameters? Like, will it be considered as auto default, or
so it does have a set of default values, so it doesn't matter even if you don't specify. So the only thing is, sometimes you might find the picture to be smaller, sometimes it might be larger. So in order to prevent that from happening, we just pre-specify this to a certain value so that it is convenient for us to look at. That's it.
I have one more question, that plot style 538, does it tells like line chart or something, or what does it does the style refers to?
No, I'll show you the difference. So right now I'm just not using that 538 style. Okay, now I'll just skip that line for now. Let me come back to it. Okay.
Yeah.
So now let's just assume that we have defined the charts. Okay, then what I do is, next step, I'm reading in the data file. So data file is in the form of an Excel file. Of course, it's the same sample superstore data that we use in Tableau. The sample superstore. We are using this function read_excel. Okay, so if we are using a CSV file, we will be using read_CSV. If we are reading an Excel file, we'll be using read_Excel. Okay, so I'm loading this file. Now see here, so once the file has been loaded, it has 9,994 rows and 21 columns. And just to simplify things, we will just be taking the furniture category alone. Okay, so I'm just filtering the data set DF for furniture category and storing this in a new data set called furniture. Okay, so now that we have filtered the required data, we'll just see what is the duration of the data that we have. So I'm just so we have the order date column in the sample superstore data, right? So I'm just taking the minimum and the maximum of that column. So the data starts from 6th January 2014 to 30th December 2017. So we have data for almost 4 years. Okay, and I don't need all those other columns like the product category, quantity, and so on. So we'll be forecasting the sales amount. Okay, and we need only 2 columns for that. That is order date and sales. So this is if you remember, a couple of weeks back we were talking about univariate and multivariate forecasting techniques, right? So ARIMA is one of the univariate forecasting methods. Okay. So I'll just be taking these 2 columns along, date and sales value column. Okay, and in these 2 columns I will just check whether there are any null values in the data. So for that I am using this function called isNull, and it will just give me the total number of null values in each of these 2 columns. So you see, for order date columns, the number of null values is 0, and the same for the sales column also. Okay. Then it could be possible that in the furniture category there could be so many different types of furnitures, right? So on the same day, different customers might have purchased different items in the furniture category, but we are trying to forecast the sales for the furniture category overall, not for the individual products in that furniture category. Okay, so we just need to aggregate it at the day level. Okay, so for that I'm just grouping the data by this order date column, and I'm summing the sales value. Okay, so now just see, so from the 9,994 we filtered out for furniture. Okay, and that gave us around 2,000 odd rows. And when I have aggregated the sales by the date for the 2,000 odd rows, I am getting only 889 rows. So now if you just open this data set and see, for each day you will have only one observation: 6th Jan, 7th Jan, 10th Jan, 11th Jan, like that. So for each day you have the total sales amount. Okay. And I will just make this order date as index. So this is just a requisite for us to use the time series function. That's it. Okay. Now we are using this function called as resample here. Now we used the same function last week. Okay, and the reason we used it was the data we needed to aggregate it at a daily level. Okay, so last week, if you remember, we were looking at the number of people who rode on the metro rail at every hour of the day. Okay, and we said we don't need to forecast at an hourly level, we need to forecast at a daily level. Okay, so we just aggregated that hourly data into a daily data. Okay, we just increased or decreased the granularity of the data from hourly to daily. The same thing we are doing here. Okay, we are having one observation for each day. Okay, but we are just taking the average daily sales for a particular month. Okay, and I'll tell you why are we doing that. That is because our data is at irregular intervals of time. So we have 6th Jan, 7th Jan. We don't have the data for 8th and 9th Jan. Okay, and then we have 10th and 11th Jan. We don't have the data for 12th Jan. Okay, now if you just refresh your memory, one of the prerequisites that we told for time series forecasting was that the data should be at regular intervals of time. Okay, so if it is daily, means it should be there for every day. If it is monthly, means it should be there for every month. Okay, so there should not be any gaps in the time series data. So that is why we are aggregating this data at a monthly level. And since we don't have the data for some of the days in each month, we are just taking the average daily sales for a particular month. Okay, so I'm just taking the average, and so this MS is basically a notation for months. So it is a predefined notation available in Python. I'm just aggregating the sales value at a monthly level, and I'm taking the average. Okay, so just see, I'm putting this in a new variable called as y, and it has only 48 rows. Okay, so that is, we had data for 4 years, 12 months in each year, so 12 into 4 will give you 48. Okay, so now you see we have one row for January, one row for February, one row for March, and so on. Okay. And this shows you the average daily sales for that particular month. Okay. So now I will come to visualizing the time series. Okay, so I'll just visualize this aggregated data. Now just see here. You can just go to plots. Now this is how this data set or this visualization looks like. Okay. Now I'll just show you the difference between this using this 538 and not using this 538. I'm just running this piece of code again. I'm not sure why I'm not getting. So typically what happens, I think maybe I missed a line or something here, but what happens when you use this 538 piece of code is it will show you this plot in a gray shade in the background, with the gray shade in the background. I'm not sure, I was getting it yesterday, it's not working this morning. I'm not sure whether I missed a particular line of code in the middle, but basically it's a style format that you use for formatting your the way your plot looks. That's what it does.
Okay, so like where we are telling like we would like to view in a line chart, is there any piece of code which insists or time series by default it will take line chart?
So by default this will take the format of a line chart. So the dot plot function by default it plots a trend line. So there are additional parameters which you can specify inside this plot function if you want to show the graph in some other design. Hello?
We can hear you, sir.
Yeah, okay. Yeah. So now that we have visualized how the time series looks, the next step is to separate the different components of the time series, the trend component, the seasonal component, and the noise component, and see how each of those three components looks like. Okay, so for that I'm using this function called seasonal decompose. It's an additive time series. Again, just contrast additive series versus multiplicative series. Multiplicative series means the amplitude of these variations increase over time. Okay, but now you can see that it has remained relatively stable. So that is why we are using an additive model. So I'm just running this block of code here. Yeah, now you can see the first plot that you see here is the actual time series plot which you saw in the previous picture. Okay, the second part is the trend component of the time series. So you see that up from 2014 July to 2015 July it has an increasing trend. Okay, and from 2015 July to around 2015 December or November it has a decreasing trend. Then again it is increasing. So like this, in different frames of time, the trend is either increasing or decreasing. Okay, and then there is a seasonal component as well, which is like I think towards the end of the year it peaks, before which there is a trough, and then before that there is a smaller peak. So this pattern, the seasonal pattern, repeats for every year. Okay, so that is what we have. And then there is a noise component, which is a random component which does not have any pattern. So that is what these dots over here indicate. Okay. So now we have decomposed the time series into the different components. Okay, and then the next step is to perform the augmented Dickey-Fuller test to see whether the data is stationary or not. Okay, so for that you will be using this function called AD-Fuller. So just remember, we imported that package called AD-Fuller, and I'm just applying that AD-Fuller function on this y variable. Okay, and let's just see what the test results look like. Yeah, so the rest of the line is just for displaying the results in a readable format. Okay, so if you just perform this AD-Fuller test, then it will not, so it will just list down these values, and it will be hard for us to identify which value stands for what measure. So for that, we are just specifying these parameters over here, and then we are using a for loop and displaying the parameters of the results one by one. Okay, that's what we are doing. And you can just see the p-value over here. This point, I think 9 preceded by 5 zeros. Okay, now the way you use this AD-Fuller test is you look at this p-value. If this p-value is less than 0.05, then it means the data is stationary. Okay, if it is greater than or equal to 0.05, then it means the data is not stationary. Okay, so here since the value is less than 0.05, the data is stationary. In case it is not stationary, then you will have to apply that log transformation or that square root transformation to make that stationary, and then proceed with your model. Okay. Yeah. So now that you have identified that your data is stationary, you will just proceed for building the ARIMA model. For building the ARIMA model, you need to determine the parameters of the model, that is the P, D, and Q values. Okay. And like I said, we will be using an iterative structure, and in each iteration we will try out different combinations of this of each of this P, D, and Q, and for each of those combinations we will calculate that AIC value, and we will choose that combination which has the minimum AIC value. Okay, and I'm just specifying for P, D, and Q, we will just take the values of 0, 1, and 2. Okay, for these three values we'll be taking the different combinations, and we'll be checking out the AIC values. Okay, so the remainder of this code is basically where for each of those values it performs that iteration to give you that AIC value. I'm just displaying the AIC value here using this print function. Okay, so no need to go too much into the details of this code. I don't want to confuse you here, but basically this is the functionality of that code. Okay, now just observe what happens when I run this piece of code. Yeah, so now you see here, we have, if you just scroll up a bit here, it will see for each combination of that P, D, and Q, it will calculate that AIC value. Okay, and at the end, if you see, it displays the minimum AIC value, that is 283. Okay, and the PDQ values corresponding to the AIC value of 283 is 1, 1, 1. Okay, that is what you see here. All right. Now there is one additional component that Python allows you to specify when you are building this ARIMA model, that is called as seasonal order. Okay, now the seasonal order basically takes this additional parameter called as S, where S is the periodicity. Okay, so this periodicity basically is the frequency of the data that you have. So if you have quarterly data, then you specify 4. If you have monthly data, you specify 12. If you have daily data, you specify 365, and so on. Okay, now we aggregated the data at a monthly level, right? So we will be specifying S is equal to 12. Okay, so in this, so this is a function which you are importing from this particular package called as this SMTSA state space, this SARIMAX function. Okay, we'll be applying this function on this Y data set, and the PDQ values are 1, 1, 1. And along with the PDQ values, you are specifying the periodicity. Since we are using the monthly level data, we are specifying the value of 12. Okay. Now, stationarity, we are saying it is false because the data is already stationary. So you don't have to enforce the stationarity here. We are saying it is false. And then invertibility is also false. Invertibility is, so the stationarity corresponds to that auto-regressive component. Okay. So I told you this time series ARIMA has 3 components: auto-regressive component, integrated component, and moving average component. Okay, autoregressive component has something called a stationarity. The same thing for the moving average component is called as the invertibility. So let us say I provide the comments here. Invertibility is the counterpart to stationary for the moving average part of the process. Okay. And let's just build the model with the parameters that we have identified. Yeah, so now we have built the model, and we are just in the next step we are just fitting the model onto our data to see what it looks like. Okay, and then I am comparing the actual and predicted values. Okay, so just run this line of code. Here, if you say I'm using a function called as conf_int, basically this indicates the confidence level of our predictions. But if you don't specify anything, the default confidence level is 95%. Okay, and let's just see what the predictions look like. Yeah. So what we have done is we have predicted, or so we have modeled the time series on this data, and we are comparing the actual values and the predicted values for the last 1 year. That is the 2017, from 2017 January to 2017 December. We are comparing the actual values and the forecast values. The blue line basically indicates the actual values, and the orange line indicates the forecast values. The gray shaded area indicates confidence interval. So basically it says for a 95% confidence, I can say that the value can range between this particular value, it's just over 1000 and 1020 or 1000, something like that. I can't, the exact number you can zoom in and identify, or you can just display the results. But so it ranges from somewhere like 1020 or 1050 and to a minimum of I think it's around it's a little over 400. Okay, so with the 95% confidence, I can say that the value can range between this 1050 and 400. Okay, so the higher your confidence level, the wider this interval will be. Okay, that is one thing to remember here. Okay, but the forecast values or the single forecast values determined by this orange line that you see here. Okay, and since you compare the actual and the forecast values, you just measure the accuracy of our model. Okay, so I'm just storing these two values, forecast values and the actual values, in two separate variables, and I'm using the mean absolute percentage error to compare those two values, truth values and the forecast values. Let's see what that looks like. Yeah, so I'm getting an accuracy of 77%. So industry standards typically 80% is a very good level of accuracy. Okay, if you've gotten a very high level of accuracy like 90 or 95%, it probably means you've overfit your model. 80% is decent. We have obtained 77%, but of course this is just this might not be real-time data. This could be dummy data, the sample superstore data. Okay, and using this model, we predict the values for the next 1 year. Okay, so it is how will the sales numbers look like for 2018. Okay, so steps is equal to 12 is where I specify for the next 12 periods, or for the next 12 months, get the forecast for the sales value. Okay, and we will plot these results, see what it looks like. Yeah, so we had data for the 4 years, right, from 2014 to 2017. Now, using this data, we have trained the ARIMA model, and we have, using that ARIMA model, we have forecast the sales values for the 2018. Okay. And again, the gray shaded area indicates the confidence interval. Okay, so this is how you implement the ARIMA model for time series forecasting in Python. Okay, now the trick here, right, in any time series forecasting is figuring out those parameters. All right. Now, if you have previously worked in time series, you might have come across a situation where you might have built your model, okay, but all that forecast will give you is one straight line. Okay, so it will give you a flat straight line, or it will give you an increasing straight line or a decreasing straight line. It will not forecast the time series with this trend and seasonality combined. Okay, so that is the most difficult or the challenging part of the time series forecasting. Okay, so that is where we use that AIC method and iteratively find out the right parameters for that forecast, and then we make that forecast based on those parameters. Okay, I have given a reference link also in my code here. I will share this code with you along with that data file, and you can just go through this code on your own and get back to me if you have any questions. And please feel free to tweak the parameters of the model. You can just play with the code, tweak those PDQ values, see how this changes and so on. Okay. Any questions, doubts, clarifications?
Yes, we have given a range 0 to 2. Like, how to choose, or does this have any implications in the output?
Yes, it has. So basically, you're saying, so if I specify the value of P as 1, right? It means just the immediately preceding observation alone has an impact on the current observation, or just the previous data alone has an impact on the current period's data.
When you mean previous, like previous 1 year alone, or
one year or 1 month, based on whatever frequency you have.
Okay.
So that is what you call as an auto-regressive or auto-correlation part of the data. So based on that previous or preceding period or correlation period that you specify, accordingly the forecast measure or the forecasted value will vary. Same goes for the Q value or the moving average value as well. Depending on the length of that moving window you specify, the forecast value will be different.
Okay.
And the way we have done this, we have tried out different combinations of that P, D, and Q, and we are saying this particular set is best because the AIC value is the lowest, and AIC value is lowest because it loses the minimum amount of information. So that is how we determine those parameters.
So basically, range should be less than or equal to number of years data we are passing, right?
Number of years. Yeah, it should be contained within the data set, right?
Yeah.
So if we have data for, let's say, 10 years, then number of preceding periods should be less than that.
Yeah.
Obviously. Yeah.
Understood. And one more question, like based on this, like P values, the data will be more focused. Like for example, if we are passing 3 or 4 years data, and will it take the most recent data, like more important, for example, in the analysis or whatever model, 50% from the previous year, 25 from the 1 year, like that?
No, so it does not apply a weightage. So this ARIMA model does not apply a weight to the previous period's data. So that is something what the exponential smoothing model does. So what the exponential smoothing model does is it assigns weights on those preceding observations, and those weights decrease exponentially with time. So this one, it just considers the data. So this entire approach is called as a Boggs-Jenkins approach. So this is different from the exponential smoothing approach in that it does not apply the weights to the preceding observations.
Yeah, that's all from my side. So.
Any other questions? Okay.